Hi, this is Alex from devstories.eu. PyTorch Fundamentals, Episode 4 of 18. Training a neural network means calculating the derivative of your error with respect to millions of parameters. Doing that by hand would require pages of calculus and constant rewriting every time you change your model architecture. PyTorch solves this by tracking your mouth in the background, a concept known as the magic of Autograd. Autograd is PyTorch's built-in differentiation engine. It automatically computes gradients for any computational graph. To see how it works, picture a standard linear transformation. You have an input tensor containing your data, a weight matrix, and a bias vector. The goal is to compute an output, compare it to the actual target value, and calculate the error or loss. Your input data is fixed, so you do not need its derivatives, but the weight and bias tensors need to be updated later, meaning you absolutely need their gradients. You signal this to PyTorch by setting a flag called requiresGrad to true when you create those parameter tensors. This tells the Autograd engine to start watching them. When you perform operations on these watched tensors, multiplying the input by the weights, adding the bias, and calculating the final loss, PyTorch does two things at once. It computes the actual numerical result, and simultaneously, it constructs a directed acyclic graph, or DAG. In this graph, your starting tensors are the leaves, and the mathematical operations you applied are the roots. Every new tensor created by an operation has an attribute that stores a reference to the function that created it. This tells Autograd exactly how to compute the derivative for that specific mathematical step. This graph is not a static structure defined at the start of your script. PyTorch builds the DAG dynamically from scratch during every single iteration. When you run a forward pass, a brand new graph is constructed on the fly. This dynamic execution means your network can change its behavior on every step. You can use standard Python control flow like if statements or loops, and the engine will cleanly track whatever path the data actually took during that specific run. Once your forward pass produces the final loss tensor, you trigger the gradient calculation by calling the backward method on that loss. Autograd immediately traverses the graph in reverse. It uses the chain rule to calculate the derivatives of the loss with respect to every tensor that has requiresGrad set to true. It then takes those calculated values and stores them in the grad attribute of your weight and bias tensors. The complex calculus is completely abstracted away. There are times when you only want to push data through the model without calculating gradients, such as when evaluating a trained model. Tracking history requires extra memory and computation. You can stop Autograd from building the graph entirely by wrapping your code block in the Torch NoGrad context manager. This temporarily stops the tracking and executes the math much faster. The true power of Autograd is that it turns arbitrary Python code into a fully differentiable mathematical structure without you ever having to manually write the derivative formulas. Thanks for listening. Take care, everyone.